Okay, the fourth and final installment of this lecture, we're going to talk about pH and pOH. Okay, so concentrations of hydronium ion can be measured directly to determine how acidic or basic a solution may be. Or, the real quick way of doing it is looking at the pH scale. It is used as a simple alternative, and it is actually a shorter way of demonstrating what acid it is, or how acidic or how basic it is. Okay, and this is based on a logarithmic scale. And so the hydronium ion can be slightly higher than 1 times 10 to the negative 1th molar, or even as small as 1 times 10 to the negative 14th molar. And so the scale is used to represent very high and very low concentrations on a graph. And to show exponential changes on a graph, because it's not linear, it's exponential, we use logarithms for that. And so the pH, the idea behind it is when the ion concentration increases by 10, the pH goes down by 1. When the hydronium ion increases by 100, or 10 to the second, the pH goes down by 2. Okay, and remember, 10 to the second equals 100. Okay, so, for example, if the water's pH is 10 to the negative, well, so water, for example, it has a hydronium concentration of 1 times 10 to the negative 7th. Its pH then is this number without the negative, pH of 7. If the hydronium concentration is 1 times 10 to the negative 4th, then the pH is going to be 4, that number without the negative. So this one's going to be what? This one's going to be 3. Okay, this one's going to be 2. And this one is going to be, look at that, negative 12 is going to be 12. Now, that's why I want to ask you guys, what about oh, it's not there. What if you have a number that is, what about pH, or what about numbers in between? For example, 3.0 times 10 to the negative 3, say. Okay. Well, if this is actually a number that we're looking for, then know that 3.0 is going to be in between 1 times 10 to the negative 3 and 1 times 10 to the negative 2, because negative 2 is actually a larger number than 10 to the negative 3. So what we would get then is a pH that is in between 3 and 2. Okay, because 3.0 times 10 negative 3 fits in there, we're going to have a pH somewhere in between 3 and 2. Say like 2.7 maybe. Okay, so as these numbers increase, it goes in between our pH numbers in here. Okay, so here's how we calculate pH and pOH. The pH is this. It is the negative log of the hydronium concentration. To do this, you will need a scientific calculator. If you do not have a scientific calculator, you don't need to do this. For the STAR test, you don't need to do it on the STAR test. You'll need to know pH, but you won't need to know in between numbers. They would give you 1 times 10 to the something, so the pH will come out even. Or maybe the difference between 3 times 10 to the negative third and 3 times 10 to the negative second, which would be a tenfold increase. So it would just be an increase of 1. Okay, or POH is the same way, except it's for hydroxide instead of hydronium. Now, the pH and the POH are always 14 when you add them together, which should make sense because if the water, where are you? Here you go. Actually, it's on the previous page. Because the concentration of the two molarities, this is going to have a pH of 7. This is going to have with a pH of 7 and a POH of 7. The two of them together are going to add up to 14. So, same thing over here. pH and POH are always going to add up to 14. Now, how do we measure pH? We measure pH using the indicators that we mentioned before. They change colors within a specific predicted pH range. So, as the pH changes, so does the color. So, for example, phenolphthalein, which we're going to show right here. Here's our phenolphthalein. It changes from colorless to pink, okay, within the pH range of 7 to 9, somewhere in there. Okay, now pH test papers, like litmus paper, you might have seen this before. Okay, forget about this part. Okay, litmus then have indicators that are actually soaked and dried on them. But the most effective way of doing it is actually using a pH probe, which is able to detect the electrolytic capability of the solution, and so by running electricity through it, and so that is where the probe is going to be the most accurate. Okay, and then finally we have buffers. In a buffer, you just need to know they exist, but we don't need to really figure them out. A buffer is a solution mixture. Ooh, did I screw that one up? That should be an X. Oh well. I'm sure you guys can fix that. A buffer is a solution mixture that is able to release or absorb hydronium ions. And this is what keeps the solution's pH stable. And they are made by mixing conjugate acid and base pairs. And that is what a buffer does. And that's the end for chapter 19. So now that you got this, get to work.